Hello everybody, my name is Josh Gonzalez, and this is my presentation on new test validation of serum beta-2 microglobulin on the Beckman-Coulter AU-5800. A little overview of this presentation. We'll go over what method validation is, why we do it. I'll introduce you to our analyte and the instrument that we'll be using, as well as how Huntington Hospital will validate a new test, which is the meat of the presentation. So what is method validation and why do we do it? Method validation is a multi-step process that a clinical lab can use to assess a method or assay and make sure that it can be used in that specific clinical lab. It's also a process that clinical labs can use to make sure that a assay meets specific standards and regulations that the lab themselves set, and also standards and regulations by organizations such as CLIA or CAP. In short, it's like testing the test. So why do we do method validation? Well, we're trying to answer the big question, is this method reliable enough to be used in our clinical laboratory? And I've gone ahead and underlined and bolded the word reliable because, after all, the results that we get from these machines are being used to aid in the diagnosis of patients. So as a clinical laboratory, we would want our assays and our methodologies to be as reliable as possible. Now I'll introduce you to the analyte I chose, the clinical instrument or the analyzer that we'll be using, as well as the methodology of this assay. The analyte that I chose is a protein called Beta-2 microglobulin. It's a small protein that can be found on the surface of nucleated cells. You can also find it in bodily fluids such as serum, urine, and even synovial fluid. It's a component of a major histocompatibility class 1 molecule. Significant levels of this protein in the serum are nonspecific markers for diseases such as kidney and liver disease, inflammation, and the big one, cancers such as multiple myeloma, leukemia, and lymphoma, as the proliferation of certain cells causes an increase of this protein in the serum. So this leads us to applications of measuring serum beta-2 microglobulin, one of which is setting up screens for kidney or liver disease. You can set up a screen for cancer as well. Another big use is therapeutic monitoring of cancer patients. You can measure the amount of serum beta-2 microglobulin and see how it goes down as the patients who have cancer get treated with chemotherapy. The analyzer that we'll be using is the Beckman-Coulter AU-5800. It's an instrument that can handle a high volume of patient samples. You can set it up for automation. It has several different reagents for carrying out different clinical chemistry assays, and its main methodologies are the use of the ISE, or an ion selective electrode, as well as photometric assays, which is the measurement of light in certain clinical chemistry assays. Here's a picture of the AU-5800 at Huntington Hospital. On the left is the manual loading rack. In the middle is the ISE, and to the right is where the photometric portion of the instrument is. This little computer is actually the user interface of the instrument. Operation of this instrument is actually relatively simple. You have to take a rack and then put your patient samples on it. Make sure the barcode faces forward. Then you go back to the machine, place the rack in the manual loading rack, and then go ahead and press play. Then the instrument will take your samples, it will go into the machine and do all the reactions necessary to get a reading for your analyte. The machine actually knows which test to run based on the barcode that's on the patient sample, which is an excellent segue into our methodology. It's called immunoturbidimetry. It has two parts, the immuno part and the turbidimetry part. I'll discuss the turbidimetry part first. And turbidimetry is essentially the measurement of light intensity when you shine it through a sample. The immuno part is a little bit more complicated. This assay makes use of a reagent that has latex particles that are coated with an antibody that is specific to our analyte, or our antigen, which is beta-2 microglobulin. The basis of the methodology is that the analyte will react with these latex particles that have antibodies on them. They will form immune complexes, and the instrument will shine a light through the reaction vessel, and depending on how many immune complexes have formed, based on the concentration of beta-2 microglobulin, the light that actually passes through will have a lower intensity, and this is picked up by the sensor. So in summary, the higher concentration there is of beta-2 microglobulin in the sample, the more immune complexes form in the reaction vessel, which means more light scatter. The more light scatter means there is a less intense light reading. So in other words, the amount of N light is inversely proportional to the light intensity reading. And based on the light intensity reading that the machine gets, it can use that intensity reading to calculate the amount of beta-2 microglobulin in the sample, giving us a quantitative result. Okay, so before we head into the meat of the presentation, we'll have a short 15-second break. You can go ahead and pause, grab some water or a snack. Okay, I hope your break was a good one. Now we'll be going into the actual method validation process with our analytes, our analyzer, as well as the methodology. So a few things need to be considered before the method validation process even begins, and that's feasibility, cost analysis, and the use case of the assay. And these entail why the test needs to be run, and usually a physician would want the test to be run in the lab. How much the test will cost the lab to be run in terms of reagents and QC and calibrators. Will the test ultimately make the hospital money, because the hospital is a business at the end of the day? And other considerations such as training individuals to run the test. So for the purposes of our validation, we'll say that we want to be able to monitor the treatment of cancer patients in the hospital. And for the sake of time, we'll just say that the lab can afford to run the test. So here's the pre-flight checklist for the method validation, and the details of the method validation are decided in this sort of step. Here's where we decide what the type of test we're going to be running, the target population of our assay, the type of reagents, QC materials, standards, and calibrators that we'll be using, as well as the exact specimen type that we will be running the assay on. Usually the guidelines for these details are provided by the manufacturer, and since the manufacturer is the one that manufactures the instruments, labs will generally follow the guidelines that are set for these tests. So the test is quantitative. We want our target population to be cancer patients. We're going to be using Beckman-Coulter reagents, QCs, calibrators, standards, and our specimen type would be serum. So now that those details are decided, we can start on the method validation. This validation process is actually based on the Huntington Hospital Standard Operating Procedures, which is in turn based on the CLSI guidelines for method validation. So the first step in our method validation is determining the analytical accuracy of our assay. In other words, how close is a obtained value from the actual true value? And this is done using a correlation study, either from a method that was used previously in the lab, or in our case, what we will be doing is comparing results from our assay with another laboratory running the same assay and the same patient results. We will have 40 samples that are tested in duplicate over a 5-day period, and the data from this study is analyzed. So what we've done is taken serum beta-2 microglobulin values from 40 samples, cancer patients, from normal patients, and also from controls, and we've graphed the values that we've gotten from our new assay that we're trying to validate versus the assay of an established lab, an outside lab. And we've graphed them on a linear regression graph with a best fit line. We've also made a bias plot, which is the deviation of an obtained value from the true value. And we've also calculated certain things such as the correlation coefficient, the t-test, and the slope, which are all markers of the relationship between the two values, because you are running the same patients. So for time's sake, let's say that these values are within the acceptable parameters set by the lab, and we'll move on to the next step. So the next step is assessing the analytical precision of our assay, which is how close certain values agree. We'll be running at least 2 levels of control, but in our situation we might choose to do 3 because cancer patients have an increased amount of serum beta-2 microglobulin. These are basically running at the levels of control repeatedly and then measuring the mean, the standard deviation, and also the coefficient of variation, which are all different means of assessing the precision of an assay. This is usually done on one day, and then another precision run is done on different days of the week to prove that the machine can run on a singular day and also be precise across an entire week. The next 2 steps are determining the analytical sensitivity as well as any analytical interferences. These 2 steps are usually determined by the manufacturer representative, meaning that the manufacturer themselves will state the sensitivity for an assay as well as any interferences that an assay might have. Analytical sensitivity is useful in assays in which there needs to be a differentiation between a zero or a blank sample and then a sample of very low concentration. In our case, this doesn't really apply, so we'll skip this step. And then for analytical interferences, the manufacturer will usually document any cases of interferences for certain assays, and it's the laboratory's job to document in the standard operating procedures what potential interferences may occur, as well as to make sure that they avoid running samples that contain the specified interferences. The next step is determining the analytical measuring range, or the AMR, of an assay. These are the upper and lower limits of the assay's ability to report results. This is usually stated by the manufacturer, and the laboratory will take it upon themselves to run a verification of the AMR through a linearity test. So here we have the AMR linearity verification example. This is very similar to the correlation test for determining analytical accuracy, except in this case what we're really concerned about is across the analytical measuring range, which is the lower and the upper limits of the measuring ability of the assay, are they consistently accurate so that you can verify the analytical measuring range stated by the manufacturer. And this can be done by checking the bias between the different uh, expected and obtained values, as well as things like the slope coefficient, as well as the correlation coefficient. And last but not least, we have our reference range verification. Reference range is defined as the normal or the healthy range of an analyte in a certain population, but reference ranges can actually be subjective to depending on what you're measuring. In our case, if you want to establish a reference range for the measurement of serum beta-2 microglobulin, we would have to establish a new reference range, as cancer patients will already have elevated levels of this protein in their body. And for therapeutic monitoring purposes, we want to be able to establish a certain threshold that we want to meet. So a new reference range would be necessary. So that would entail gathering patients who fall within a certain range and then evaluating the data to establish the new reference range. Ultimately, the fate of our method validation lies in the hands of the laboratory director, as well as the guidelines set by CAP and CLIA. And the laboratory director has to review all the graphs and plots and data that we have made and decides whether it's good enough for the lab to run and whether the assay has been validated. And so we can answer yes or no to our original question, is the assay or method reliable enough to be run in our lab? And if it's a yes, congratulations! Good luck on your CAP surveys. Thank you for watching my presentation. Hopefully I didn't bore you too much. Stay tuned for the 5 questions and answers that I have prepared for you. Here's my list of references and also image credits that I've used throughout the PowerPoint. So the first question I have for you is, what is the clinical significance of levels of serum beta-2 microglobulin? And the answer is that elevated levels can mean liver or kidney disease, inflammation, and marked levels of elevation can also point to cancer as well. The second question is, true or false? In immunoturbidimetry, analyte concentration is directly proportional to light intensity reading. And that would be false. It's actually the opposite. Analyte concentration is inversely proportional to the light intensity reading because the analyte actually scatters light and provides a less intense light reading. The third question, at Huntington Hospital, what type of test is run to assess analytical accuracy? And that answer is a correlation study or a correlation test, where you have to compare two sets of data and see if they are related. The fourth question, when can a reference range for an analyte change? And the answer is, if a hospital serves a different demographic or target population, such as in our case with cancer patients, the reference range for a certain analyte can actually vary depending on the use case. And the last question is, how must manufacturer claims be treated when assessing data of an assay? And the answer to this one is that manufacturer claims must be verified by the library. You can't just take the manufacturer's word in this aspect.